Hi, today I'm going to talk about the solution for Atcoder Beginner Contest 434 problems A to E. For the first problem, we have integers W and B, and W is Takahashi's weight in kilograms, while B is the weight a single balloon can support, but then this is in grams. So we want to find the minimum number of balloons needed to make Takahashi fly into the sky. So we just need Takahashi's weight to be less than n times b, where n is the number of balloons, and it needs to be strictly less than this value. So we can just directly um, calculate for this one, and let's look at the code. So here's my code. I first inputted the values w and b, and I multiplied 1,000 by w because the unit is in kilograms, and I'm going to convert it to grams. And this part I divide by b, and this calculates the number of balloons needed, and I add 1 because it needs to be strictly greater than W. So I add 1, and this would be the answer. Next, let's look at problem B. So for problem B, there are n birds and m types of birds flying in the sky. The birds are numbered from 1 to m. The bird types are numbered from 1 to m, and the birds are numbered from 1 to n. And each bird has type AI and size BI. So we want to find for every type the average size of the birds of the current type. So for this problem, we just need to keep track of for like each type, we keep track of the total weight and the number of birds, and that way we can calculate the average weight. And here we can also look at the code. So here's my code. I first inputted the A and B, which is the type of the bird, and yeah, type A and size B. So I inputted the values for this, and then for the type array, I keep track of a pair where the first number represents the total weight of the birds in this current type, and the second number represents the number of birds we have that are type AI. And so I just when I input the values, I add this so I can keep track of in the end I would have this array that represents the M types that we have, and then for each type, the total weight and then the number of birds. And that way we can calculate the average weight. Because this is a double value, I used a printf where I print until 7 decimal places, and then I convert this to double before I divide so I can get the decimal points. Next, we have problem C. So for problem C, again, Takahashi has decided to fly in the sky with balloons, and he is at altitude h at time 0, and will fly for um 10 to the power of 9 seconds. So for each second, he can change his altitude by up to 1. So he can increase his altitude by 1 or decrease by 1. But then he cannot make his altitude like less than 0. So there are n goals regarding his altitude that he needs to meet, which are at time ti, he needs to be at least um Li of height and at most at position UI. So there's this range that he needs to meet for these n times, and we need to determine whether he can meet these goals. So let's first look at an example. So in the first example given, this is Takahashi is initially at height 5. So initially h is equal to 5, and then this is the time and the upper and lower and upper limit that he needs to meet. So these are the two goals that Takahashi needs to meet, and then it's at time 3 and time 8. So first, if we look at this, we can see that initially, if we keep track of a lower bound and upper bound that his current height may be, because like we don't know the specific value that he is, so we can keep track of a range. So like a L to R range, where it's like the possible height that he may be at this current time. So at time 0, since he is at altitude of 5, so the range that his height may be is just 5, 5. And then afterwards, um when the time becomes 3, then 3 seconds has passed. The delta t is equal to 3. So he may have decreased his height by 3 or increased his height by 3, like any value in this range. So his height is now from 2 to 8, and however, he has to meet this goal. So his height should be in the range from 1 to 4 if he wants to meet this goal. So if we make him meet this goal, and then like this is the possible values that he can have, but then if he wants to meet this goal, then his height can only be from 2 to 4, because he needs to be in the range 1 to 4. And so afterwards, now when we move on to the next goal, there's the delta t is equal to 5. So 5 seconds have already passed. And if he like the possible values he can have are from -3 to 9, where -3 comes from like 2 minus 5 is -3, and then 4 plus 5 is 9. So these are the possible values that he can be at. But then because he needs to meet this goal of being in the range from 9 to 11, then his only possibility is this. So next, we can look at another example. So the next example is if his initial height is at 6, then again, let's look at this example. Initially, his range would be from 6 to 6, and after 1 second, he may be at the range 5 to 7. However, he needs to be in the range 1 to 4. So this is impossible. So what we would do is um because like we first always compute the possible range he's at, if he doesn't have to meet these goals, and then we check the range he can be in if he wants to meet these goals. So if he wants to meet the goal, because he's in like 5 to 7, then this is impossible to meet the goal. So we will output no. And so after these two examples, we can see that the way we want to solve the problem is that we should keep track of a LR for each range, and we can just check if it's possible. So if for each goal needs is at time ti li with lower bound li and upper bound ui, then when we update our L and R, this is min. So when we update our L and R for L, we would have L minus Ti, where L is like the previous height, and then delta T is the change in time. So this is the distance he could have decreased in this time. And we find the maximum with Li because uh he needs to be at least at a height of Li if he wants to meet the goal. So we would find the maximum, and this would be the lower bound. And to update the upper bound, we just do the opposite, where we for R we add delta T, which is the maximum possible value he could have increased his height by. But then it needs to be no less than this upper bound because he needs to be in this range. So if L is greater than R, it means that it's impossible because the lower bound is greater than the upper bound. So there's no possible value that he could that could allow him to satisfy this goal. So we can just output no. And if at the end there's still a valid range, so L is still less than or equal to R, then we will output yes. So that's the case for this part where like when we actually calculate the range, um we will have 5 and 4 where 5 is greater than 4, so this is impossible because uh there's like no valid range. And now let's look at the code. So this is my code, and I put my results in like this function called solve because it makes it simpler to keep track. And this is my initial range. So for each test case, I input the values. My initial range is just HH, and then pre-t records my previous time. So that way I can like find the change in time, which I use the variable dt to record the delta t. So I used a pair of integers to keep track of my range, so my lower bound and upper bound, and this is how I update my range as I mentioned previously. And so if the range lower bound is greater than the upper bound, then the answer is false. But then one thing to note is that we can't just like directly output no and then return because that would mess up the input. So we still need to take all the inputs before we can output the answer. So that's one thing to note here. Moving on to problem D, we have the sky is currently represented by a 2000 times 2000 grid, and when we um look up at the sky, they're like different cells and they're labeled as um RC, whereas the um cell from at the rth row from the top and cth column from the left. There are also N clouds that are currently floating in the sky as different rectangles, and they cover the different cells. So what we want to answer is that if we remove, for each of the clouds, if we remove only that cell, um, how many cells are not covered by any cloud? So for the first example, it's like the clouds are all different rectangle, and if we like remove the first cloud, um these cells would not be covered and we would output the answer. So let's look more in depth at how we can solve this problem. So first, taking the example in the problem. So here I just labeled these cells like by how many clouds are covering the current cell. So um these grids all have only one cloud covering it. So which means that if we remove rectangle one, then these grids would change from being covered to not covered. So this would affect our answer, and we can calculate our answer if we know this value, like if we know that um these 7 cells are not going to be covered, then we can calculate our answer because initially we can keep track of a variable called total. And this will represent the total number of cells that are covered. So in our case, this would be like this whole range that's covered. So however many cells this is, I believe this is 24 in this case. Um I'm not really sure, but I think it's 24. And for each rectangle, if we know this value, so if we know that there are 7 cells that are not covered, then we can know that if we remove the first rectangle, the number of cells that are covered would be total minus um so um the total number of cells covered minus the ones that are covered only by this current rectangle would be the number of cells that are covered if we remove this rectangle, which is what we're trying to find because we're actually trying to find the number of cells that are not covered, but then we can just do like 2,000 times 2,000, which is the total number of grids minus this value, then we would get our answer. So now how can we find this value quickly, like the number of cells that are covered only by this current rectangle? So this is what we're trying to find. And first, if we want to update the grid to like this value quickly, where we have the number of rectangles that are covering this current cell, we can use a 2D prefix sum. So if we use a 2D prefix sum, we can get this value, and then since we want the grids that are only covered by one rectangle, so these grids, then we can transform it into another grid where we only record these values. So like these cells that only are covered by one rectangle. And if we do another prefix sum, then we would get another grid that has like these sums. And then that would allow us to quickly calculate for any like rectangle here the number of ones in this area. So if we do another prefix sum, we can quickly calculate in this range, there's like 6 ones, and then this would correspond to this rectangle. So for each rectangle, we would be able to quickly calculate the answer. And here, let's go over how to do a 2D prefix sum. So if we have this um, grid here, and then these are like the grid lines, and we have the prefix sum called sum ij. which represents our 2D prefix sum. To update, when we're first updating the values for the prefix sum, we would do this where plus we would plus if our current grid is ij, then we would plus I minus 1j, which would be this value, so like the value here, and ij minus 1 would be the value here. However, the value in like this section is updated twice, so we would subtract this again. So this is kind of like the inclusion exclusion where we would subtract this like over counted region again. So this is how we would um update our value for prefix sum. And so if we want to um if we have this rectangle and we first want to update the value so we can get like this grid, then the values we update would be, we will add 1 in this position because we want these values to all have like add 1, and we will subtract 1 both here because the rectangle stops here. So if this blue rectangle is what we want to update, we will add 1 here, subtract 1 here, and then again, because these have like already -2, so we need to add 1 again here to avoid like subtracting twice. So this is how we can update the rectangle, I mean. So we will update these values and then we will do prefix sum. And after we do like this sum on the values we updated here. So when we input the rectangle, we can update these values according to the rectangle. And then when we do prefix sum, we will get this, where it's like the number of rectangles that are currently covering this grid. And then we can then put this on another array to record only the values that have ones. And then we can do prefix sum again. So now we can quickly find the number of ones in any given rectangle. So how to get the values in a rectangle quickly? So like when we have this sum, we want to find the like value in any rectangle quickly. So so if we want to find the value again in this rectangle, pretend this is like a prefix sum matrix, then it would be sum dr, because sum dr would be the sum from here, like the sum of ones all up here, because prefix sum records the values from top left to the current position. So like anything above here. And then we have to subtract dl minus 1. dl minus 1 will be any value like here. So we subtract this part, and then we have to subtract u minus 1r, which is any value in this region. And then again, in this region, as in like anything here. And then again, we would need to add back this value, which is L, u minus 1, L minus 1, because this part is subtracted twice. So we again add this back, and now we have the value in this rectangular region. So to summarize what we need to do for this question, we need to first use prefix sum to calculate the number of rectangles that cover each cell. So this is this matrix that we will obtain. So this matrix is first. And then we need to do prefix sum again, this time on the number of cells only covered by one rectangle. So we will get this matrix, and then we will do prefix sum again on this matrix. Then for each rectangle, we will find the number of cells that are only covered by that rectangle using prefix sum. So we would quickly get that value using this prefix sum formula, and we would know the number of cells that are only covered by that rectangle. And now let's look at the code. So here is my code. This is UDLR, the values I inputted, and then this is my grid. So my grid would store the values that like for each cell, the number of rectangles that cover that cell. And so here I update the values according to what I mentioned. Um, and then so like UL would be plus, while UR plus 1 would be minus, and then we would add back the value that is subtracted twice. So now we update this part is like updating my prefix sum grid, like to store the first set of values, which is the first matrix that I mentioned, that stores the number of rectangles covering the current cell, like all the cells. And then we would update our second matrix, which is now only the cells that are covered by only one rectangle. So I put this in a array called sum, and I would update this value. So then I also I also need to store a value called total, which is the total number of grids that are like covered by a cloud. So that way I can like update my answer later. And now I do another prefix sum, this time on the number of grids, the number of cells that only have one cloud covering it. So then here I can quickly calculate for each cloud. I loop through from 0 to n, like for each cloud, the like for that rectangle, how many grids are only covered by that cloud. So I can quickly calculate based on my prefix sum, so I can like subtract the values and then add back u minus 1, l minus 1, as I mentioned. And the count would be the number of cells that are only covered by the current rectangle that we're on. So now we can calculate our answer, which is 2000 times 2000 is the total number of grids, and then total is the number of cells that are covered by any rectangle, like before we removed a rectangle. And count is the number of cells that would not be covered by um that would now not be covered by any cloud if we remove this rectangle. So like total minus count is the current number of cells that are covered, and this this minus this will be equal to our answer, which is the number of cells that are not covered. Moving on to the last problem. For problem E, we have n rabbits numbered from numbered 1 to n on a number line. And rabbit I is at coordinate xi, and multiple rabbits can be at the same coordinate. They all have a um parameter called a jumping power, and they have a jumping power of ri, meaning that they can jump to coordinate x plus r or x minus r. So now if we can choose which coordinate each rabbit jumps to, we want to find the maximum possible number of distinct coordinates after all the rabbits have jumped. So for example, in the first case, we have these values. This is the initial position the rabbit is at, and then this is like their jumping power. the second value is their jumping power. So they can move to these values, and then this would achieve 3 distinct coordinates. So again, for the first example, what we can do is we can look at this as a graph. So this is the first example, and position 1, position 2 is the positions, the 2 positions that each rabbit can get to after they've jumped. So like x minus r and x plus r, and these are the regions. So if we like make this a graph and then we connect the values, we would get this graph. And since each rabbit can only jump to one location, this would be equal to kind of like coloring the graph, where for each edge we color one of the nodes. So for the first edge, maybe we can color this node. And for the second edge, we can color this node. And for the third edge, we can color this node. So three nodes can be colored, which corresponds to the number of positions uh that we can put rabbits to. So like we would have 3 distinct coordinates that have rabbits. And now we look at a second example. So this is the second example, and then this is like the initial x, and this is r, the jumping power. So again, this is like x minus r and x plus r. And if we connect the position 1 and position 2, we would get this graph. And now if we do the same thing, which is like color one node, then we can see that if we start coloring from this first edge and this first edge, we color this node. The second edge, we color node 3. And then this edge, we color node 7. And this edge, we color node 5. And we can see that all these edges, like because there are so many edges, we would definitely color all of the possible positions. So the answer would be 4. So what we can see is that in this case, the graph is a tree, and there are 4 nodes, so only 3 can be colored. So, and in this case, it's like the graph has more edges than nodes, so it's like not a tree. When it's not a tree, all of the nodes can be colored. So now, after looking at these 2 examples, let's see how we can do this problem. So, first we would connect the edges, like between position 1 and position 2, which is the 2 possible positions that each rabbit can end up at. So we connect the positions each rabbit can be at and allow that to form a graph. And so this graph may have different components. So maybe this and this is like in the same graph, but then they just have different components because these 2 are not connected. So then we then need to like, for each component, we need to check whether it's a tree or not. So this is a tree and this is like not a tree. And so for each component, we will need to check like this condition, because this would determine the number of vertices that can be colored. So what we want to do is for each edge we color one vertex, and if the current component is a tree, then n minus 1 vertices can be colored, where n is the number of vertices in that current component. And otherwise, if it's like not a tree where the edges is greater than n minus 1, then all the vertices can be colored. So because the coordinates the coordinate values are also large, we need to do coordinate compression, and that way we can, after coordinate compression, we can keep track of the nodes easily because they will have smaller values. And to keep track of the components, because here we need to update individual components, so we can use a disjoint set union to keep track of these components. And we can see how to implement this in my code. So now let's talk about the code. So first I inputted the values x and r, and I put them in this vector called points. So I can use coordinate compression. So I would do coordinate compression on this like vector. So I push all the nodes that we have, so all the values here, x minus r and x plus r, I would push this into my vector, and then I would sort the vector and erase all the like repeated elements. So now we would have this array points where it's like sorted in order and they're all unique elements, and that would allow us to do coordinate compression. And I created a map called old to new where it maps the old index to the new index. So here is the old value mapped to the new value here. And then I will update the um, number of edges that are connected to each node. So the reason we need to do this is that if we want to check whether a a component is a tree, we can keep track of two things, and the first would be the number of nodes that are like in that component, and then the second would be the number of edges. So if the number of edges is greater than or equal to the number of nodes, then that would mean that it's not a tree. Otherwise it would be a tree because a tree is like a graph where there's n nodes and n minus one edges. So that's why we need to keep track of the edges. So I have this unordered map. It maps the current vertex. The first value stores the current vertex, and then the second value stores the number of edges that are connected to this vertex. And here, so we update the values, and then because I'm using this part is my disjoint set union code, and then I just unite these two nodes. These are all like new nodes after we've done coordinate compression. So I would just unite these two nodes together. Then now I would update the values for each component. So the two values we need, the total number of edges and the number of nodes for each component. And I stored this in another map of it maps the component index to a pair where the pair stores the number of edges and the number of nodes in that component. And here I use DSU to quickly find the root node for each component, and then I just updated the values here until maybe I can move this. Yeah, so now this is in order, and um the first value represents the total number of edges, so I would add the number of edges here, and the second value represents the node, so I would also add one. And now we can calculate the answer. So if p dot first represents the total number of edges, and p represents the total number of nodes in each component. So p dot first divided by 2. The reason we divide by 2 is because the edges here would be the number of edges connected to the current node. So when we add here, it's like double the actual number of edges because each edge is counted twice by like the two nodes it is connected to. So that's why it's the total number of edges is doubled. So if we want to find the actual number of edges, we just divide by 2. And if it's greater than or equal to the node, then it's not a tree, and we would add the number of vertices in this component to the answer. And otherwise, it would be a tree, and that means we can only color n minus 1 vertices. So we would add p dot second minus 1 to the answer. And in the end, we just output the answer. Thank you for listening to today's explanation.